Hello, ladies and gentlemen. Scott the Nerd here. One thing I've been wanting to talk about is I've been wanting to talk about the Atwood device. Um, and we've been using it a lot in class, and those of you who are my AP students, you'll know that I didn't do a very good job of explaining it today. We kind of did it up with an equation that didn't make a lot of sense, and so I've thought about it and I've simplified my explanation a bit. Now, the reason we like the Atwood device as sort of a scenario is because we can use this setup to describe also kind of what happens when an object falls and let's say pulls another object up a ramp. Or it's also helpful in describing what happens with this sort of scenario where we have a cart being pulled by a falling mass across the surface. Anyway, that's something we're doing in my other physics classes right now. But what I really want to do, let me expand the screen a little bit here. What I really want to do is break it down as basically as possible without plugging in any numbers. Okay, kind of get a generic rule for everything here. So, first course of action is always a drawing, which we have here, and followed by a free body diagram. So in the free body diagram, I haven't really specified this much yet, but in an AP test, they only want to see the forces in your free body diagram. They don't want me putting mg in for the force of gravity. What they want is they want you to literally put F sub g for the force of gravity, at least on the free body diagram. Once we get to the sum of forces, we can start breaking things up all we want. Okay, and we know that what's opposing the force of gravity in this situation is the tension. Okay, and I would normally write T1 and T2, but we know that this tension here, pulling this up, is the same tension here, and they're also in the same direction. This one's pulling up, this one's pulling up. All right. Okay, there it is. Now, sum of forces. We know the sum of the forces. Okay, and I'm going to say on M1, so I'm going to do M1 in my subtext here, is equal to the tension force plus the force of gravity. Now at this point I am going to break it down. I'm going to say M1 times G, and at this point it's going to be equal to whatever the force is, whatever the total force is going upward. Now if there is no force, this equation still works, it's just the answer is 0. But in this case, the sum of the forces does not equal 0. We're going to say it equals something in the upward direction. So I'm going to write M1 A1. Okay, and we're going to say this is up and this is down, and you'll see why I'm saying that here in a moment. Okay, so I'm going to box in this formula for right now. Okay, and now what we're going to do is we're going to sum the forces on the second situation. Okay, same thing. Free body diagram. Okay, tension's still up, but it's up from this one's perspective. And remember, we're dealing with third law pairs, so it's only things that are interacting directly with the object that we're drawing the free body diagram for. I could care less what's happening up here, down here. And once again, we're also pretending as though the string is massless, because you can imagine if it wasn't, as this string went over the top, it would be adding mass to this side, and it'd mess up the whole problem. And so in physics, we like to pretend we're suffocating, sliding around on ice, and all strings are massless. And it simplifies things. We'll add in mass strings, non-slippery objects for frictional surfaces, and air resistance when we get to later on. But for right now, just to make it so we learn the absolutely fundamental physics, we get rid of all the distractors. And in this case, the mass of the string is a distractor. All right, so some of the forces on this guy is tension, still up, and then the force of gravity down. Okay, and I'm actually going to put a 1 here and a 2 here because the force is going to be different, being that the masses are different. All right, so sum of the forces for mass 2. Now, of course, it's only in the y direction. We have nothing in the x, so I'm just going to pretend x doesn't exist on this problem, is equal to the tension plus mass 1 times gravity equals mass 1 as you were, not mass 1, mass 2 times acceleration 2. Now, I'm going to quickly change that. Hopefully you guys can see what I'm talking about on the screen there. Yeah, you can. Okay, good. Acceleration 2, the reason it's a different acceleration is this one's pointing downwards because it's falling down, and this one's accelerating upwards. So even though they should be the same number, the magnitude, the directions are opposite. Okay, this kind of messed me up today when I was teaching, because I was like, well, they're technically the same, but they're not the same. I want to get to one acceleration as a solution. How do I fix that? Well, all I do is I'm going to replace A2 with negative A1, and then I'm going to multiply the negative off right at the beginning. And so we end up with the final force being negative mass 2 times acceleration 1. Look, now we can solve for this. Okay, so I'm going to box in this formula. Okay, the next part of this is we need to combine these formulas. Okay, easiest way to do that, solve for t, and then plug in that entire new formula in for t, and then we'll simplify and try to get acceleration out of the formula. Okay, and so this is pretty much a system of equations here, right? At this point we have two unknowns, so we need two equations, right? All right, so, well, to simplify things, I'm going to get rid of the drawing. I might add it back here in a minute. But I want to make sure we have lots of room so you guys can see the rest of my mathematical wizardry here. All right, so T plus M1G equals M1A1. Okay, this is for the sum of the forces for mass 1. What I'm going to do is I'm going to move this over, so we get T equals M1A1 minus M1G. Now my first instinct tells me I want to pull M1 out of that, but we're not going to do that. We'll just leave it like that for right now, make life a little easier later on. Okay, and in the other formula, what I'm going to do the same thing to the second formula. I'm actually going to solve for t. That way we can set the two equations equal to each other. So we end up with t plus m2g equals negative m2a1, right? Because it's negative. Remember, it was in the opposite direction. And we're just going to move this over. This becomes negative m2g. So just subtracted this over there, got rid of it. Okay, now I'm going to plug in this for t. So we get m1a1 minus m1g equals negative m2a1 minus m2g. So at this point, you see we have an acceleration here, gravity here, acceleration here, gravity here. Let's separate, let's say divide and conquer, basically. So moving this over here, we end up with m1a1 plus m2a2, and we're of course going to move this over here, and we end up with equals m1g minus m2g. All right, everything's stable at this point. Oh, by the way, I put m, it's a1, right? The same acceleration. And you notice the negative went away when I moved it back over here. So now we have something really helpful here. So I'm going to pull a1 out front, a1, and put m1 plus m2 right here. And that equals, I'm going to pull g out in front of this, g times m1 minus m2. Okay, and in order to get rid of this, I got to move it over there, and I'm going to have a solution for a1. So a1, acceleration 1, keep forgetting to put my vector here, that's a direction, equals g times m1 minus m2 divided by m1 plus m2. Now, the magic of the Atwood device, the magic of this situation is, the only things I need to know that final acceleration of the falling object is masses. We all know what gravity is, at least on here, little g, 9.81. So as long as I know the masses of my objects, I will know the acceleration, and therefore I don't actually need to go out there and hang objects from an Atwood device. Now, of course, we do that in class because we want to make sure, we always want to prove that this formula actually works, which is what we've been doing.